Hello, ma'am.
Yes, ma'am.
Ma'am, am I audible?
Yes, ma'am, you are audible.
Okay. And moreover, I want to just have a check. My screen, whatever slide I am now projecting, is it visible?
Yes, ma'am. Yes, ma'am. Development of first order Thevenin
Thank you,
space.
ma'am. So kind of you. Okay.
Okay, ma'am. Shall we start, ma'am?
Sure, ma'am.
Okay. Good morning, everyone. Myself, Dr. Patil Monica, Assistant Professor, Triple E Department, Vardhaman College of Engineering. On behalf of Electrical and Electronics Engineering Department, I welcome everyone for this 1 week IEEE sponsored online FDP on applications of power electronic converters to power and energy systems. The objective for this FDP is to provide a unique and national level opportunity to an in-depth discussion on the various challenges and their possible remedies of recent trends and applications on power electronic converter topologies, converter design, controller strategies for inverter design, and also discusses the grid integration with multi-level inverter. This program is expected to accelerate the ongoing research activities at various institutes and industries. Besides, this FDP will provide an opportunity for the faculty and research scholars to have an interaction with the renowned experts in the area of power electronic converters and multi-level inverters. Today, we have our resource person, Dr. S.Tamil Selvi Garu, Associate Professor, Triple E Department, Assistant College of Engineering.
Thank you, ma'am. So good morning, everybody.
Systems
Thanks.
Engineering from Madurai Kamaraju University, Madurai in 1999 and 2002 respectively, and awarded PhD degree in distribution transformer design using evolutionary algorithms under Anna University in 2015. Currently, Dr. S. Tamil Selvi Garu is with the Department of Electrical and Electronics Engineering, SSN College of Engineering, Tamil Nadu, serving as an associate professor since 2016. She has over 17 years of work experience, including 10 years of teaching experience, 2 years of industry experience, and 4 years of full time research experience. She has worked in various places, including Sri Venkateshwara College of Engineering, KLN College of Engineering, St. Joseph College of Engineering, Tagore Engineering College, and many more. Dr. S. Tamil Selvi Garu has published her research work in 15 SCI lists in international journals and 3 international conferences. She has published 2 books and 3 chapters. She has published her software code for NSGA2, a multi-objective revolutionary algorithm in Matlab Central to serve the research community. Her fields of interest include is evolutionary algorithm applications to power system operation, transformer design and optimization problems. Dr. S. Tamil Selvi Garu is a resource person for several STTPs, FDPs. Dr. S. Tamil Selvi Garu also received travel fellowship from UGC and AICT for her research paper together with IEEE 2002 held at University of Stanford, UK, and also Excellency Award for the research paper titled Multi-Objective Revolutionary Evolutionary Computation elsewhere. Thank you, ma'am, for giving your valuable time. Now you can start your session.
Thank you, ma'am.
Thank you, ma'am.
Thank you for the introduction. Okay. I think introduction is enough, and I can straight away jump into the topic of today's discussion. And today, this is a slide I'm sharing. Hope everyone is able to view that. Okay.
Yes, ma'am.
Okay. So it is all about modeling a battery. So before going to talk about how to model a battery, first we should know what is the use of modeling a battery. Because we know that if you take any battery, it is now getting increased penetration rate in every battery system, something like electric vehicle, mobiles, and what else? Laptops, uh, everywhere. We cannot find any even small e-systems without a battery. Am I right? So there is an increasing penetration rate everywhere across globe. So definitely we should have an accurate battery lifetime prediction for the systems what has been in use. So what is that lifetime prediction? Because we are using a battery. Definitely a customer who is buying a battery will be interested to know what is the lifetime of the battery he may have after it is put in use. So how to predict that life of the battery? So that is a big question mark. Manufacturer may know how many cycles it would come, how many charge discharge no scenarios it would come, but the customer may not know. So how are you going to predict the lifetime? How are you going to estimate the lifetime and help the customer to avoid the range anxiety problem whenever he is no in an electric vehicle on ride? Because that is I think you understand whenever no we are riding in an electric vehicle with a battery systems, definitely there would be a range anxiety. So how long this battery would survive? So we may not know that. So definitely modeling of the battery will play a vital, crucial role in every battery systems. I think now you understand the use of battery modeling. So use of battery modeling, no? Battery modeling is necessary, essential. Why? Because without which we cannot predict the lifetime of the battery. And moreover, you know that in every battery systems, like whatever I said, no, vehicles or laptops or phones or whatever, wherever we have got a battery, there is going to be some monitoring system as well. So this battery monitoring system, what it would do behind the screen, it would monitor the state of the system, state of the battery, condition of the battery, parameters of the battery. So it is something like studying the state of charge, depth of discharge, health of the battery. Okay, what else? There are several other parameters to add in, something like temperature. I think you are able to follow what I come to say. So the conditions of the battery are very much essential to follow up in order to come up with the life of the battery and cycles that are done with the battery. Okay. So now you may think that for battery monitoring system, we can very much dependent on the sensors. No, it is not possible. Definitely, we cannot measure all of these parameters by using sensors. That is the drawback and bottleneck what we have in order to have an efficient battery management system. That is the real issue everyone face with the battery management system. So if you take a battery monitoring system, which is a battery management system, we are completely dependent on state estimators instead of the sensors. So what are the state estimators? That is where this battery modeling methods, techniques play a role. So now we are going to see next, what are the battery modeling estimators available? See, there are different methodologies, different approaches to bring this modeling. What is this actually modeling? Yes, now you understood what is the use of modeling. Where is this modeling being applied? Am I right? In order to estimate the life of the battery. Done. Now, what is this modeling as such? Modeling is nothing but getting the charging characteristics and discharging characteristics of a battery for a different charging rate and discharging rate for any cycle. Say manufacturer may provide you the charging characteristic and discharging characteristics for some cycle, say cycle equal to 1, cycle equal to 20, cycle equal to 40. Say a charging rate is equal to 0.5 CR, discharging rate 1 DR. He may not be able to give you for the different charging rates, discharging rates, and at no any future cycles also. Am I right? So Now it is necessary to have a model that is going to get us the scenarios, charging scenario and discharging scenario of a battery for any rate and for any cycle. I think you are able to follow me. Manufacturer can give us the model, but still we work on the battery model. Still we find some approach to develop a model because the model that are provided along with the battery by the manufacturer has some limitation. That is all an experimental data. Yes, I agree. That is all an accurate data. Yes, I agree. But still, that doesn't come for all the batteries and that doesn't remain same for every battery. Though all the batteries are manufactured by the same manufacturer and
Excuse
all
me,
of
ma'am.
them. Yes,
Sorry
ma'am.
for the disturbance.
Yes, ma'am.
Slides are not changing, ma'am. Can
Yes,
you
I'm
please?
not changing. I have not gotten to the topic.
Okay.
Okay. Still I'm justifying the title of the first slide.
Okay.
Done.
Okay.
So that is why always a modeling or approach is what is the right approach to be used for making a model is also very much important. I think you are able to follow. Now next comes what are the approaches available. I have not given much slide in that. I have straight away going into my proposed approach in order to make you understand how to develop a model in that. But before that I want to give you a brief introduction about the use of model, what are the different approaches available for modeling also. So what are the different modeling approaches available now? So basically we have some kind of, because you know what the battery is. It is a one which is transforming the energy from electrical form to a chemical form and naturally from chemical form to electrical form, something like that. Is it not? So, but if you look at the battery model, there are approaches with chemical form and electrical form, mathematical form, physical form, and also the recent techniques, data-driven techniques like what is that? Machine learning models and optimization algorithms. So there are several approaches. If you take one after the other, there are no drawbacks as well as the positive points in every method. If you take electrochemical modeling, modeling can be developed with that electrochemical approach also, but the maker or the modeler, the designer should have a deep in-depth knowledge in solving several partial differential equations which are quite cumbersome and tedious and time consuming. Okay, so that is why we don't simply go for electrochemical modeling. Then comes the physical modeling, mathematical modeling. So those models are able to what is that? Mimic the battery systems, but still it is not so accurate. Okay. And coming to the next model, what is called as electrical model is the one what I am going to deal today. So I think now you are able to see the next slide, what I am throwing now. Do you able to see that electrical model? Madam, can anyone reply me so that I can go further?
Yeah, ma'am.
Right. So now we are going to discuss about this model. So there are several approaches available to model, to have a model. Electrochemical, now I'm skipping that. Physical model, I'm skipping. And other, no. What else? What are the other models we have? Mathematical model, again, I'm skipping. And now I'm going into the electrical model. Even in electrical model, it is all about resistance capacitance network models because we are electrical engineers. We are good in dealing the circuit analysis, so we are considering this electrical model. We call it circuit oriented modeling approach for developing the battery charging discharging scenarios. So now I'm going to teach you how to develop a model, how to develop a charging characteristics and discharging characteristics with a circuit oriented RC network using evolutionary algorithms. Okay, so now here I have given you some three figures, so with which you can understand what are the possible RC networks we can expect to have in order to develop a model. You can even go with a simple model with only resistance. What is that CVS? It is an internal voltage source. Okay, then next come a simple, I mean little complex than a simple resistance model, that is first order RC model. It consists of the internal resistance, source resistance, RS. Along with that, we have one RC pair, resistance and capacitance. Okay, why do you have to have this resistance capacitance? Because I want to know the transient behavior of the battery. Battery as such, you know that every battery is different. Though all the batteries are having the same, what is that, manufacturing tag, same capacity, same ampere hour specifications, rating, but still the behavior is completely different. No, coming to the battery, that is why we should study about the transient behavior of the battery, not only the steady state, because it is completely non-linear in nature. So practically it is not possible to avoid this transient behavior. That is why with a simple resistance model we cannot have an accurate transient behavior of the battery. So we have to add a little more complexity in order to have the accurate model. So now I have this figure B shows the first order model. So we can definitely have a battery model with this equivalent circuit also. Next, we can have one more no order to add in, that is second order circuit model. So we have got R1C1 pair along with that in series with R2C2 parallel network. So likewise, we can have n order no RC network also to have a better accurate predictable battery model. Now for today's discussion, I am considering the single order, first order RC circuit. So here we have got a circuit. I'm going to teach you how to start with modeling. So before modeling, we should definitely have the circuit with us. So now I have got one simple resistance R1, then one RC pair. Then I've got two terminal no voltages. One is the internal voltage source, other one is the terminal voltage. Okay. So now, what is this model? I said already we have to have charging scenario, discharging scenario, charging characteristics, discharging character. What is the charging characteristics? Charging characteristic is nothing but a curve or I can put it in this way. Uh, Characteristics, what is this characteristics? If you want me to define a characteristic of a person, how would you define? He behaves this way, this is his feature. So something, no, we simply define a person with this no behavior characteristics. Something similar to that, we can define a characteristics of a battery also. Okay, so now here, how are you going to define the charging characteristics? So here we need to have SOC, state of charging along x-axis, and rise of voltage along y-axis. Charging voltage along y-axis. So as I increase the state of charge, as I keep charging the battery, now I can follow up the changes in the voltage that is developed, that is impressed across the internal battery system. So here I can develop a relationship between the state of charge SOC and the voltage across the battery. Okay. So now that is what is called as charging characteristics. I'll show you the graph also. See here, to be able to see a graph, I have shown you different charging characteristics, colored waveforms, colored plots. In x-axis we have SOC, and y-axis we have charging voltage, and I have different colors. So that color is to distinct the different charging rate. Similarly, the other next plot is showing the falling voltage. So that is the discharging voltage from the battery whenever the battery is connected to a load. See, sometimes battery can act as a load, sometimes a battery can act as a source. When it is acting as a source, no, it will give voltage. When it is acting as a, what is that, load, then it will take the power from the source, is it not? So you can charge as well as discharge with a battery. So while discharging, what happens? Uh, then you will replace the state of charging with the depth of discharge. So along x-axis we will have depth of discharge, along y-axis we will have the discharging voltage. And here also you can have sequence of curves or plots. So all those distinct colors, different colors are given to know the different discharging rates. Okay. I think now you can catch me with the point what I really intend to tell. So now what do I come to tell? Uh, charging discharging characteristics na modeling na I am going to develop that curve. That much is the outcome of this discussion. So at the end of the class you will learn how to develop that plot for different charging rate. Okay, so now how are you going to bring that? Okay, done. Next is to know about the internal structure of the battery. So now we are assuming that battery has got an equivalent circuit in this form, something like this, where you have got one resistance and RC parallel network in series. Clear? Am I right? Then you should know what is the relationship between this R1, I mean internal parameters of the battery like R1, R2, C1 and the voltage source, internal voltage source V0 and the battery terminal voltage VBC. Battery terminal voltage V suffix BC denotes battery terminal voltage. Okay. Suffix C denotes charging scenario. Okay. I will replace this C by D if at all this terminal voltage is for the discharging scenario. So here this equivalent circuit, this electrical circuit which is analyzed, studied, simplified, reduced using Thevenin's theorem, which we have learned in under what is that lower semester classes, and we have obtained these relationships between state of charge, charging rate, and the internal parameters like resistances and capacitance, and the internal circuit voltage, internal voltage source V0 of the battery. Can you understand the battery parameters now? The battery parameters are nothing but RC network parameters. Okay. So now we are going to charge the battery. While charging happens, this voltage, no terminal voltage is available across the battery. So now we are able to analyze this electrical circuit using Thevenin's theorem, Thevenin's model. There are several electrical models available also. I will tell you, list you that also. So we have simple resistance model, RC model, EIS model, electrochemical inspection model, EIS, spectroscopy model, EIS, inspection spectroscopy, electrochemical inspection spectroscopy, that is Warburg impedance spectroscopy model, then runtime models, then we have Thevenin model, then we have sometimes combined model. There are several electrical models also. Among these models, the one which is so simple and so accurate and compatible with the experimental results are nothing but our RC models. Okay, and in RC models also we have several order models, and among n order models we are considering the first order model under consideration. Okay, for some application, any electrical vehicle or any application under study. So now as a first step, we should definitely have a modeling equations relationship between the internal parameters of the battery and the terminal voltage of the battery. That is the first step. Very first step is to decide which approach to bring in. So having selected the approach, whether first order model or second order model or whichever model, then we have to identify what are the battery parameters available like R1, R2, C2. Then suppose if you're going to have one more RC network, then you will have R3, C2 also in picture. So then you may have to have two more equations also. All these equations are polynomial equations. If you look at the equations, these equations vary as a function of CR. CR is a charging rate. See here, it is an exponential equation. If you look at the first term, you can find out A1 plus A2 CR plus A3 CR squared. Followed by that, we have no E power minus A into SOC. So this parameter, it is a function of charging rate CR and SOC, which is a state of charge. Similarly, there is a relationship for every other battery parameter also. How we have to obtain it? This is one PhD work. You can take it up Even you can see, this is the first order equivalent circuit. You can make it as your research work, PhD work, if at all you want to develop a battery model using a second order Thevenin's model. Also you can have third order model also. You can develop such equations, you can develop some mathematical modeling for this black box. Black box is our battery. We do not know about whatever that is happening inside the battery. Simply I'm charging, simply I'm putting that battery under a supply. I really do not know what chemical action that happens inside the battery, but still this electrical input, it is getting converted to a chemical form, and now I am now transforming or assuming or interpreting those chemical what is that reactions that are taking place inside in the form of equivalent electrical equivalent circuit as a circuit oriented model with these kind of equations, which is a function of the charging rate and the state of charge. So I think now I make sense. So what are the other parameters which I have to disclose now? Q is the capacity, that is an ampere hour. C is the capacitance. IC, capital I suffix C is the charging current, and other RC are the internal parameters of the battery, and small t, it is the time of charging. TC is the time of charging. The same equations we can have for the discharging scenario also. So now I have changed the slide. So this is also again same battery parameter, but now the scenario is going to be discharging. Okay, so either you can have the battery to perform as a load or as a source. Depending upon that, you may have to take the voltage, or you may have to what is that, give voltage. So now this terminal voltage is no longer VBC, it is VBD, and it is no longer TC, it is TD, which is discharging time. Okay, so IC is replaced by ID, and TC is replaced by TD. I think now I make sense. So now what else I missed to explain are the polynomial coefficients. So what are they? You know about CR in charging scenario, and here I have replaced it with DR, which is discharging rate. And now what else is left unexplained? They are the polynomial coefficients, A1, A2, A3, A4. Do you able to see all of those A's A1 till A31? So how many parameters right now I have in my hand? A31, A1 to A31. They are called as polynomial coefficients. Battery parameters are RG parameters and internal CVS, voltage source, and CRDR are rates, charging discharging rates. Okay, SOC DOD are SOC, state of charge and depth of discharge, which a battery monitoring system has to monitor with this state estimator. Now next comes the battery parameter extraction process. How am I going to extract this battery parameter? Because now I have shown you a parameter of the battery. Now my aim is to develop a battery model, in the sense I have to plot charging curve and discharging curve on my own for any battery under consideration at any charging discharging rate for any nth cycle or ith cycle. Okay, then how am I going to do? What is the solution method I'm going to use? Before I was talking about the approach I have to use for developing a model. Now I have decided to have an electrical model. Now next comes the solution method to extract the battery parameters. So what is that? So now here I'm going to use data driven approach. See, in today's world, if you look at the emerging techniques, we have two data driven technique. One is black box modeling, other one is gray box modeling. Black box modeling doesn't require any mathematical equations for study. Simply it is sufficient to give the data at hand. So if you provide, this is the input data and output data, and you train the network, black network, some architecture using machine learning systems, or any neural network system, then you would be able to have no output when modeling curves for charging and discharging patterns. Okay, and without having any mathematical equations, something in the form of what is that, A1 to A31, which is which is little complicated. We call it black box technique, for which we should know how to have a model, how to train the model, how to test the model, and how to improve, increase the accuracy, of all of that. Clear. And moreover, validation is necessary. How are you going to validate the charging discharging patterns? Okay, so that also is a next big headache, because we do not know about the prediction accuracy, because it is all about prediction. What is the use of developing a battery model? Next we are going to predict the lifetime of the battery, am I right? In just next task is to understand the capacity fading. To start with, at the first cycle I have 80 ampere battery in my hand. After some 40th cycle I cannot expect the same 8 ampere hour capacity in my hand. It is now no, some capacity is found lost. So it is because of several other parameters. We are not going to dwell on that, but still I should definitely know what is that fading of the capacity, what is that correct lifetime of the battery at that nth cycle. So for that only we are breaking our head to understand the modeling. Now again this battery modeling also is little inaccurate. Again little prediction process where I'm not sure whether it is accurate or not. Validation is still necessary. Then again it would be little confusing. Okay. So for that again we can be dependent on some more approach also. Instead of having one approach to have a model, you have one more approach. Compare these two and still have the experimental manufacturer catalog scenarios also. Compare with that also, then you will be able to validate whichever algorithm, whichever methodology will suit best for this solution of battery modeling problem. Okay, so now I tell you, after having conducted several analysis, I've got that this optimization technique, that too with an evolutionary approach, is well uh, suit this battery modeling problem, and it can attend it with better accuracy. So what is this all about? You know much about the evolutionary process. I think I don't again have to waste your time in that, but still I tell you one thing. You take any solution problem, very simple problem first we take. F is equal to x squared. Okay, F is equal to x squared. Now my objective is to find a value of x such that this f is maximum. Okay, then what I will do, I will substitute a value for x. This something I will keep substituting, and I will checking the value of f. So it is going to be enumerative process. It can take any value of x, and I have to keep substituting on that x squared equation and finding the f. So similarly, it is going to be a little time consuming process. We call it dynamic programming approach. Okay, manually if you're going to sit and solve such problem, it is going to give an accurate result finally, but how many days you are going to work on such function f? Okay, that's the question. And moreover, if that function is going to be an exponential function, if that function is going to be having a multivariable dimension, f is equal to x squared has got only one variable. If it has got n variables, if the dimension is heavy, see in our problem, what is the dimension? 31. I have a1, a2, a3, a4, so on till a31. I have to find out appropriate values for all these a's such that my function objective is met. I have not so far disclosed what my objective is. Let us wait there. But now I am correlating with this f is equal to x squared with the r problem right away. You should definitely map that here. This x is what is called as a design variable. So we have got 31 variables to optimize. I am interested, modeling is nothing but finding the, what is that? Extracting values for these polynomial coefficients a1 to a31 using evolutionary algorithm. So now what we do in this evolution, see without evolutionary algorithm, what we do for f is equal to x squared, we will do that first derivative dy by dx, then we will find second derivative, we will check if it is greater than 0. Such things we have done even in to find out the maxima minima problem we have used in our schooling life, is it not? Again, that is not possible with this equations, because uh, these equations are derivative free equations. We do not know whether we can find out derivative for all these battery equations also. Again, that is a problem. So that's why we cannot go for a traditional method also. Traditional method, one side it's going to be complicated, on other side it's going to give accurate result, but it is going to break our head. It's going to take our time. So what do? We jump to the other method, which is so easy, user-friendly. That is that evolutionary algorithm. It uses some biological process. Okay, how normally, how every what is that? Even human being, how we evolve. We can know it is simple biological process behind this optimization. So now what really this algorithm say, no? First we start with the solution. If you take traditional method, we end with the solution. Okay, we end with solution. I solve a problem, solve a problem, mathematical problem, end only I get solution, answer. Okay, I put a box. This is answer equal to 3, something like that. But now here in this evolutionary algorithm, we start with the solution. We don't end with the solution. We start with the solution. But those solutions are not optimal, but rather they are random. So randomly I pick some 100 solution. That is what is called as population. And with that population, now I am going to call for a what you call a competition, a healthy competition among all those random solution, and I check the quality of the every solution. So every individual, every chromosome is whether good enough to take part in the recombination operation or not. I've got some 100 solution. If one solution may be good, or even sometimes 100 solution may not be good, but still I have to iterate all these solutions generation after generation to come up with one converged solution wherein I can believe that this is the final optimal solution. So it is a complete iterative technique. Okay, it is not one single generation technique. Okay, we will have n number of iterations. Okay, so to start with, we have a random solution at the first iteration with the initial population at hand. Then we check the quality of every solution in the population. That is what is called as fitness evaluation. Okay, we use objective. See, I have to find out the values for A1 to A31. Okay, such that my objective is met. What is that objective? That is the quality of the solution. Okay, so now here in our problem, what is my objective? My objective is this. My objective is, see here, manufacturer has given one charging scenario, one characteristics, meaning that uh, x-axis, y-axis, x-axis I have SOC values, y-axis I have got a set of corresponding voltage values. Okay, for every SOC, mean for every moment of state of charge, I have got a respective voltage. Say SOC 0, I have a value. SOC 0.1, I have one voltage value. So I have got some say 100 SOCs and 100 voltage values at hand at one charging rate CR. So that is provided by a manufacturer. Okay, so that set of value I have in my hand. Next, my aim is to have one equation, have one model for this 100 values. How are you going to develop a model? How are you going to have one that R1 C1 R2 C2 V naught polynomial equations? For having the polynomial equations, I should know the polynomial coefficients. Okay, so those polynomial coefficients are the what is that? Solutions. That's one solution set will have 31 answers, 31 solutions, 31 values. One set of one cross 31 is one solution. Similarly, I will have 100 solutions. Okay, so every solution will get you one f value. Like how I have f is equal to x squared, I will have one f value for that one cross 31 value. Okay, so what is that f? That f is nothing but difference in charging voltage obtained with the analytical expression, and the voltage obtained when terminal voltage of the battery that is provided by the manufacturer. See here in that expression, f of x is sum of I1 0 to n absolute and the modulus VCM minus VCC. VCM is the charging voltage measured value. VCC is the charging voltage calculated value. So this calculated value is obtained from the evolutionary process. Because I've got one solution of 1 cross 31, I substitute that 1 cross 31 because I said I am inviting a competition for every solution. I'm checking the quality of the random solution. How are you going to check now? 1 cross 131 I'm taking, and now I'm substituting in that R1C1 all that expression. I'm going to find what is this V naught. See here, I have got A1 to A31 at my hand. So now I'm able to find out R1, C1, everything. Everything will come as a number at respective CR. Okay, then I have got V0 and all the values are ready. Now I'm having the value for VBC. So this VBC is the charging voltage. Okay. Now this charging voltage, for that, what is that? Optimized set of A1 to A31 values obtained from the evolutionary process. That is this VCC. VCM is a value that is obtained from the characteristic that is provided by the manufacturer. See, this is a manufacturer catalog given by the battery producer for a particular battery. Say for one color battery 0.5 charging rate and the orange color, I take one. And I think you can understand. We can have that curve. Now I can know track SOC versus voltage for different SOCs and different voltage. I can have a vector, and now I can see the difference in voltages between calculated value and the measured value for 100 SOCs, and what is the deviation, and that deviation has to be minimized, that is F. I think you understand. Optimization is nothing but finding a value for the design variables such that the objective is minimized or maximized. So here my aim objective is to minimize the value of F. What is that F now? Deviation between the charging values of calculated, what is that? I can say simulated characteristics, okay, obtained from the evolutionary algorithm and manufacturer characteristics. Similarly, I can have another deviation for the discharging. So now this is how we check the fitness. We evaluate the fitness of every random solution, and I have as a parent. And now this parent, having found the better solution from that random solution, okay, then now next I call recombination operation to happen. We call it mutation, crossover, and such operations are different from evolutionary method to method. So in D method, there is one operation, GA method, there is one operation. So similarly, we have several methods to come. Okay, so now having applied this recombination operation, now this parent is evolved as a new children, we call it offspring. So now there is a better solution, there is a chance for the better solution to evolve from the parent to a children. Okay, so now again next I'm going to call the competition among the children to see which individual is the right individual. Every individual is having the answer for my polynomial coefficients A1 to A31. I have again got hundreds of solutions at my hand. Now again I am evaluating the fitness of every solution, and now here we call this selection as a survivor selection. Before recombination operation, we call that selection from random population as a parent selection, and here we call it as a survivor selection because now this children is, I mean, the selected children from this offspring is going to take part as the population for the next iteration. Okay. So similarly, we will have n number of iterations, and at one, I mean, generation of after generation, iteration over iteration, the solutions are enhanced, and at one point the objective F is met and it is completely minimized. Okay. So we start with the solution and we end with the optimal value. So whatever I have said, I have given here as a points. So why do we go for algorithm? What are the advantages of the algorithm? What is the fitness? How do we evaluate the fitness? How do we know what is the objective of this battery modeling? Objective function is nothing but uh, minimizing the deviation between the measured and calculated terminal voltage for both scenarios. Now this is how we formulate the problem using an. See here I have taken genetic algorithm. You can take any recent algorithm also. I have tried with several algorithms. So now my aim is to obtain the parameters of A1 to A31. See, this is the slide. See, I think you are able to follow the slide. So we have formulated, see, always how do you formulate the problem with the evolutionary problem? No? You should first line, no, give what are the parameters you want to optimize. What do you wish to have in your hand? I wish to have A1 to A31. Clear? Then next, what is the objective you want to have? You want to meet out. Objective is to minimize. So this is that. Now next comes battery specification. Now I'm going to show you what is the battery I've considered. Say I've considered one 8 ampere hour battery. Now voltage on the specification 2.5 volt, charging rate I've considered this. So now here I think you are able to see how my evolutionary algorithm has helped to have the battery modeling for the discharging characteristics. See, this is for discharging. It is 0.5 dr. So here along x-axis we have DOD, depth of discharge. Along y-axis we have that discharging voltage. So discharging, it starts from, so already I said no, it is 2.5 volt battery. See here. So here that is why voltage, it is getting drooped from 2.5 and it is going down. And this red what is that? Red dots are referring the measured voltage, and round blue dots are referring the calculated voltage by genetic algorithm. Okay. And now I think you are able to see what is the deviation. It is very less, and by proper tuning and by enhancing the algorithm, by choosing proper crossover rate, mutation rate, and analyzing the population size and using correct survivor selector method, and I think you understand all about, no, this evolutionary process behind this battery modeling scenarios, what we have obtained out of it. So by having proper tuning on that algorithm side, we will be able to reduce this even smaller deviation also, to have a better predicted what is that, charging scenario or discharging scenario very close to the experimental value. See here. So this is again the another pattern I have got for 0.5 dr, and this is all, this is for 1 dr, and this is with the other algorithm. Here I have got with CMAES, covariance matrix adaptation evolutionary strategy. Other one what I was showing is with GA, and this is the parameter polynomial coefficients we have obtained, A1 to A31. Okay, so here we have different. See, this is how we will get set of values for 1 CR, zero point 0.5 CR, similarly. And this is the characteristics here I am showing for the charging characteristics. So which is zero point 0.5 CR. So here I'm showing both whatever model, when characteristics is nothing but relationship between SOC and voltage, terminal voltage of the battery. Okay. Uh, Obtained from the evolutionary process as well as the manufacturer catalog. If you look at this, it is almost the same. There is no deviation at all, even here also. So these are the charging patterns and these are the references. Now simply uh, let me close this slide. I want to open the Matlab coding. Do you able to see the Matlab window now? Please, one of you acknowledge me. Can one of you acknowledge me?
Yes, sir.
Thank you, thank you. Thank you so
Yes, sir.
much. Thank you so much. So now I will explain you how to have a code in Matlab also. So here already I have one set of solution and I have stored in RES result for 1 CR matrix. Let me load that and show you. See here, we have this solution. Do you able to see this 1 cross 31 solution here? So these are the polynomial coefficients we have obtained from the evolutionary process. Now how to obtain this A1 to A31? It is not very difficult. It is really sufficient to have a code, something like this, which links this 31 parameter and the objective function f. I repeat, first we have to have one MATLAB code. Okay, how to obtain this A1 to A31 values, and now I'm explaining. We have to have one code that relates this input A1 to A31 to output f. Okay, I'm going to explain you the code. First, I'm using variable n. How many design variables we have? 31. Then what is the ampere hour battery? 8. What is the amps current? 8. And now here you can adjust charging rate. Here I want to work for 1. If you want to work for 0.5, then you can have 0.5. If you want to work for other 10 ampere hour battery, you can have it here. But always for first order, you will have 31 variables. Next comes the boundary constraints. So here boundary constraint now I've got 31 variables A1, A2, so on till A31. Now how the algorithm is going to search right value for 31 variables without knowing the limit. Okay, so here I have to give the boundary, lower boundary and upper boundary. So here I have given lower boundary 0.0001. Instead of 0, I am giving closer to 0. Okay, 31 variables, 31 0.0001 values. Then for upper bound, I'm limiting till 1000 also. Sometimes for some a coefficients I know that it will not go beyond 1, so I'm simply applying that constraint intellectually and reduce the searching time. So I am giving the right upper bound here. Lower bound I have chosen closer to 0, but upper bound for some variables I'm so good in selecting the upper bound. So instead of making the algorithm to search and find out the right answer giving infinity for the upper bound, I am giving the right upper boundary knowing the behavior of the battery. So here comes the engineer to work and understand the concepts of the battery also. Because if you know a person who knows only algorithm, they will be good at writing the Matlab code, but they will not be able to find out the right bounds for the design variables. So this is where an electrical design engineer or the role of a what is that battery modeling person comes in. Okay, so here I've got lower upper what is that limit. So here I've fed that, and now this is that 31 values at my hand. And now these 31 values are not, if you look at this, all these values are random values chosen between 0 and 1. But what I need is some values between 50, between 1000, between 1. So now I have to interpret those values depending upon that. So this is done with this x is equal to xl plus xu minus xl into solution. Now next comes the manufacturer data. So this is that manufacturer data. I said no, we have to have this manufacturer data for some charging discharging rates. Okay, so here I have loaded this. Actually, I have got an Excel sheet at hand. So from Excel sheet for that EIG battery, I have read the data of SOC, time, difference in time, and that manufacturer measured voltage, all of that. So now this measured voltage, time, and difference in time delta T are ready. Now having got these values, next step is to estimate the SOC. Okay, so here Coulombic current methodology is applied. For finding out the SOC, we need this equation. We need what is the current, what is the difference in time, because for time t equal to 0, there is a voltage, rise in voltage. Again, time t equal to 0.1, there is an increase in voltage. Similarly, it goes, there is an increase in current. We inject current. Okay, so now what is that current injected? It is a constant current approach, and SOC, no, we start with the initial SOC value, then we keep on increasing the what is that? We keep on what is that? Increasing the state of charge, and then state of charge is also ready. I've got some 100 values or something like that. After that, what is the next step? Na? Battery parameters R1, R2, C, V0. I said already. We have to have one MATLAB code where you should have set of equations that relates input polynomial coefficients a1 to a31 and the objective function value, fitness value f. Okay, so here I have got r1, r2, c, whatever no we have, which is a function of cr, soc, and a coefficients. Then we have this internal voltage source v0 and terminal voltage. So this vbc is nothing but the charging voltage going to be obtained from this evolutionary process. Next comes the fitness. What is the fitness? The difference in the measured value on the calculated value. So now my aim is to reduce this f. Okay, so I've given some little constraint. So that is to speed up the evolutionary search process. So this will come by practice, because since I know the boundaries exactly, so here I've given some 5 constraints also. Even without this constraints also, algorithm will give the answer, but having added this constraint in the beginning of searching process, then we will be able to approach the answer at a faster iterations, okay, at a faster rate. So now here, this is how normally now we have a code. Now I've got a code in my hand. Okay, so now I'm going to run the code. I've run the code also. I have shown you that solution also. For that solution, so what is that objective function? It is 15.88. This is a deviation. I've got some 100 points. So at every points, there would have been a deviation of 0.1, 0.2, zero point 0.3, something like that. So you add up, you have got some 15 deviation between what is that? VC and VM, measured voltage and calculated voltage. If you want, you can plot a curve and see the variations also. So I will change the axis because the axis is different. If I change the axis, you will be able to understand. Okay. I think now you can understand the difference. So this is how we can get the plot for any battery under consideration. Randomly, I've taken one solution, and for that solution, I have shown you the coding also, and I have executed that solution input A1 to A31, and I have shown you how we are able to see that objective function f and also the plot for both the curves. One is SOC versus measured value, the other one is SOC versus calculated value. Now you can still reduce this 15 deviation, 15 volt to 0.0001 volt also. I can show you the other graph, which is very closer. I've got, after optimization, I've got this curve. I am just showing you that one. There is no much deviation. Here the deviation was reduced to a very minimal value. It was 2.5 volt. Okay. I think now you can understand uh, how to write a MATLAB code for battery modeling. And next is what battery modeling is and what is the evolutionary process behind parameter extraction also. If you want, I can teach you how to obtain the same in MATLAB toolbox also. I'll show you in few minutes. I'll show you how to get this 15 point something. 1 minute. I'll show you that also. So here the same code, whatever fitness code you have at your hand, what I can do is I have written code. Okay, code is ready. I'm going to feed solution here, random solutions here. GA is going to generate solution. There is a GA toolbox available here in the MATLAB itself. It is sufficient to have only four lines we have to develop a model. Even with this, you can know obtain one paper. You can even go for your PhD also with this problem formulation. Okay, I will show you now how to use that. If you are not good in writing a MATLAB code, optimization code, if you know only battery concepts, then it is sufficient to write the fitness code and then you can use Optim tool. Okay, there is an Optim tool. I'm opening an Optim tool. அம்மா நான் இப்ப நான் ஜாயின் ஆகல, கட் ஆயிடுச்சு போல. இப்ப ஜாயின் பண்ணிருக்கேன் பாருங்களேன். சாரி. Hello. Excuse me. I did not notice that I was out of this connection. It looks.
Yes, ma'am. Yes.
I do not know where it was cut also. Okay.
The
So now,
algorithm point.
okay, no issues, no issues. I was explaining the code first of all. So people were there in that code explanation or not? Do you able to see that MATLAB window right away?
Yes, ma'am. Yes, ma'am. Now, right, we can't see, ma'am.
1 minute. Now do you able to see that MATLAB window function fitness one charge fit? Do you able to see that MATLAB code here?
No, ma'am.
One sec. I will share the window again. Now currently?
Yes, ma'am.
Yes? Okay.
Yes, ma'am.
Yes. It was left half the way or I had to, I do not know. When did I leave that? Can anyone help me out? I started the code explanation or even before that it was cut. It was in the middle of that?
Code
We
explanation.
started.
Okay, right. In few
Code
minutes I will
explanation over, ma'am.
code explanation over. No issues. We have just initialized the variables first. So we have given the number of polynomial coefficients, then the capacity of the battery Q, then the charging current and the charging rate. Then next comes the boundary constraints. So boundary I have initialized with 0.001, then with the upper boundary. Then next comes what is that solution X based on that boundary values. Next is to feed in the measured value from the manufacturer catalog for a particular charging discharging. So here for 1 CR, this is now I'm loading. Okay, suppose if you want to have for the other measured value, you can go for the other charging rates. Then next comes this SOC calculation, because having got this measured value or manufacturer values for the voltage and time and the difference in time, next comes the SOC estimation, where we are applying that, what is that, current, Coulombic current injection method. So now here we are obtaining SOC calculation. Then already I've given all of that slide with the necessary equations for internal battery parameters R1, R2, C, V naught, internal voltage source and the terminal voltage. So this is the fitness value F, wherein we are trying to minimize the deviation between the calculated value and the measured value. And here we have got some error. So this is all based on the skills what we develop in battery modeling, understanding concepts. If you want, you can have this constraint violations also, or even without that also, the searching process will still work, but that will still act as a catalytic agent, where you can have the faster iteration completion. Okay, so now actually to end up, I wanted to show you how to run this file. uh, okay, 1 minute I'll show you how to run this file. Very sorry for the inconvenience. Really, I did not notice that I was out of this net connection also. Okay, so now I'm simply running this program. I'm going to show you. Okay, what is the I've just completed this program execution. Now next come, what is that fitness value? Okay, so here fitness is about 15.8 volt. What does it refer now? See, I've got some 100 SOC points. Okay, for each SOC point, there is a value of voltage obtained from the manufacturer and also from the what is that, simulated GA technique. Okay, so these two values are compared, and we have got the difference number, and that number it is now accumulated. We have summed up, and that summed value is this 15. So what optimization process does is, so it will find the right appropriate value for A1 so on till A31 coefficients, such that this objective function OPJ fund is minimum to the core. So even 1 volt or 0 volt or something like that. Okay. So my aim is to minimize this 15. Okay. Randomly I've taken one solution and now I've run that problem, what is that Matlab code, and I've shown you what is that fitness function. Now this is done without actually optimization. This is simply I've run that exec file. Okay. So now suppose if you want to see 1 minute, if you want to see that curve, I'll show you that figure also. I have run that plot now. Be able to see the plot. So now we have got a graph for SOC versus voltage, but here we have to change the limits. Okay. So here I am changing the limits here. So now you will be able to see here, we have got two plots. Red is for measured value and blue is from that GA value and evolutionary algorithm process. So now you are able to see the difference, no deviation between the calculated and the simulated values for different SOCs at a particular charging rate. Similarly, you can have discharging rate, charging rate also. Okay. And now next, I'll minimize this window. Now I want to tell you, this is the final, uh, almost we are on the fag end. I'm going to close the session. Before that, I want to tell you how to use the Matlab toolbox for modeling the battery. Okay. So now here, let us use Optim tool here. So I'm opening the Optim toolbox. Okay. So now in this Optim toolbox, 1 minute. Let me close this because now I'm allowing the toolbox to optimize and give the polynomial coefficients. So I'm now masking my solution. If I load a result, my solution will come into the picture. Now I'm masking that, and also I have to mask this plots, final plots also. That is also masked. I've saved this file. So okay. So now I'm running this Optim tool at hand. One toolbox will open up. Okay. So now this is already popped up. I think you are able to see that. Can one person confirm me there is a toolbox opened? Please, please once again help me out.
Yes,
Yes, ma'am.
yes, ma'am.
Open. Yes, ma'am.
See
Open.
Yes,
here.
sir.
So this even a blind person who does not know how to write a genetic algorithm code in a MATLAB, even who doesn't know what genetic algorithm does, can use this toolbox very blindly and get the optimized results very easily in a few minutes. Suppose if you have that coding, MATLAB coding for battery modeling. So now it is sufficient to give GA on select pannirkenpa. So that is here. So once that GA solver is selected, here you have to give no what is that file name. So here file name is charge underscore fit underscore optimum tool. We have that file. I mean, on that file only we have written that MATLAB code. Then here I have selected the lower bound and upper bound for those 31 variables. Here I have given the number of variables. So now next in the other window here, it is sufficient to give the population size. So here I have selected 150 because randomly I am generating the solutions at hand. You know that genetic algorithm, it starts with the solution. So here I have given 150 random solutions. Now next finally, we have to give the stalling criteria. So stalling criteria na enna. So at what number of here stalling generations I've given 300. So once these things are done, next work is to start the iteration. So this is all. So now I am completing battery modeling with evolutionary algorithms in your MATLAB toolbox. Can you see the iterations that are running in front of your eyes? 38, 39, 40, 45, 46, 47, 48. So now I've set some number of iterations to go for the searching process. Algorithm, I have allowed the algorithm to search the right value, appropriate value, values for all those polynomial coefficients A1 to A31. Okay. Once that process is done, it will tell the optimization is over. Okay, let us wait for a few more minutes to complete this optimization running process. So once that is done, you will get the results for 31 polynomial coefficients. Then you can enter those coefficients in that fit code and get the plot. So now if you have doubt, you can open up. So this is the answering session. So almost we are on the fag end, final end. Nothing more to add up. Now you got how to write a code, what algorithm does behind this know optimization process and what battery modeling is, what is the significance of modeling, and how do we have a yes answer is obtained. Okay, so now finally we come. Sorry, I erased that. Now finally we will have answers no for that 31 variables down to that final value ல இங்க இருக்கும். So those values you can pick always. Okay, and take those values and again use that in this MATLAB code. So such values are obtained here and stored in this result file, and already I've shown you this is how the plots are obtained. So I'm parallelly trying to open the figure, but the other side the program also is running. I think that is why it is getting stuck. No issues. So you have any doubt, let me clarify your doubts and close the session.
Thank you, ma'am, for sharing your valuable thoughts on battery management system and discussing various methodologies for estimating the life of battery. And also you have given the great idea for the upcoming researchers to have their research work on Thevenin's model for second and third order modeling equations. And also you have clearly explained the algorithm for the battery state of charge. Thank you, ma'am. Now it's time for the queries. Participants, please unmute your mics and ask your queries.
Thank you. Please, if you have any questions, you can ask now. Even if you have uh, what is that personal doubts to raise in an algorithm process, or even apart from the battery modeling, if you have doubts in any electrical power system problems, optimization problems, you can definitely reach me out in Tamil Selvi at ssn.edu.in in future also. If you have any doubts in modeling, you can raise it now. Because I think already I'm late, 10 minutes extended it looks. Professor Karupaya there? Shall we wind up the session otherwise?
Okay, ma'am, but I think so.
Okay, thank
I
you.
think so. It's clear.
Okay, thank
Thank
you
you,
all.
ma'am.
Thanks for inviting me. Thank you so much. Thanks for all your timing, valuable timing. I think I have done justice for that. Thank you so much.
Yes,
Okay,
ma'am. Sure, ma'am. Thank you,
okay,
ma'am.
okay.
Thank you all for your participation, and I request all the participants to join for the session 2 at 1:30 p.m. Thank you.
ఆన్లైన్కి ఇప్పుడు ఇప్పుడు అనిపించింది నాకు వ్యాలిడేట్
Now I request all the participants to leave the session and join for the session 2 at 1:30 p.m.
ఫీడ్బ్యాక్ లింక్ పెట్టారా మనం
Yes, the feedback link has been
మనకమ్మా
shared in the chat box.
సబ్మిట్ అయితే
Feedback link has been shared in the chat box.
ఓకే బాగా మేడమా మేడం ఏమంటామా అయిపోయిందా ఇప్పుడు